So we have a pulley here with a string attached to it, and there's a force of tension acting on the string which makes the pulley turn. The pulley has a radius of 33 centimeters and 4 kilograms. So we're given that the force of tension is described by the function 3t minus 0.2t squared. And that tension is given in newtons, where t is equal to time in seconds that you're pulling the string for. So our goal is to find the linear speed of the rim, a point on the rim, 8 seconds after starting from rest. So as you're pulling it at 8 seconds, they want to find the speed of a point on the rim at 8 seconds. So we know torque equals Fr cosine theta, and torque equals I alpha. Alpha is angular acceleration. So we can write angular acceleration as change in angular velocity over change in time. So we can rewrite this equation as torque equals I d omega dt. So we have d omega dt equals torque over I, as we just bring the I to this side by dividing. And we know torque equals Fr cosine theta, so that's here. The force that we're given for tension, we just plug that in for force here, and R was R0 up here. And we know the string is pulling tangentially to the pulley, so cosine theta is equal to cosine 90, which is this one. If we can integrate this equation, d omega dt equals that. If we integrate it, we get omega equals radius over moment of inertia times the integral, or the antiderivative of this function, which is this right here. And now we just plug in our values. R naught equals 0.33 meters. And moment of inertia for a cylindrical disk is 1/2 mr squared. So if we plug that into our equation at t equals 8 seconds, because that's our that's what we're trying to find, speed at 8 seconds, we get the angular velocity to be 30.303 radians per second, and our linear velocity is defined as angular velocity times the radius. So if we do that, we get that times our radius, and we get the tangential velocity, the linear velocity, to be 10 meters per second.